Welcome back to a course on calculus. Let us have a quick recap of what we have seen in the previous lecture. We have started with a review of a definite interval. That is how we got the integral values from the concept of Riemann-Son, and with the help of that, we have extended the ideas to the double integrals. So double integrals are done with respect to two variables. So if we are dealing with one variable, we take a interval and split the interval. Here we are talking about two-dimensional thing. So we take some two-dimensional space. In each axis we take an interval. So it is going to contribute a rectangle, and the rectangle is split into several subrectangles. So in each several subrectangle, we find the volume of a cuboid. So with the help of the volume of a cuboid, we calculate the total volume. So that is what. So whenever we have a positive valued function, the double integral can be treated as a volume of the surface, right? With that idea, we have done these calculations, and we have actually defined what do we mean by double integral. Mathematically, we have defined the double integral with the help of a double Riemann sum, right? And we have worked out few problems, and with the help of the midpoint rule also we have done. Here the sample point shall be taken from anywhere on the rectangle, right? What if it is taken on the upper right corner? What if it is taken on the upper left corner? And what if it is taken in the mid of the rectangle? And all these things we have done in the previous class. And the other problem that we have done is, since we know the double integral may be treated as a volume of a required surface, with that idea also we can evaluate the given interval. This is what we have seen in the previous lecture. Now we are about to see the concept of average value. Whenever you are asked to find out an average value of a continuous function, if it is average value of a discrete values, we just sum the given values and divide by the total number of values. That is going to give us the average thing. But whenever the function is continuous, which means we are having a continuous values, we'll have to find out the average of those continuous values. In that case, we will have to take the integral. We'll have to find out the integral value of the function over the given limit and divide by the length of the interval. That is going to give you the average of a function. So this one we know for sure, right? So this is what we have in Riemann integral. Now we are going to extend this idea to double integrals. If we have to find out a average value of a function which is defined with the help of two variables, okay? That is, if we have to find out the average value of a function of two variables, how are we going to do it? First of all, we'll have to evaluate the integral over the rectangle, over the specified rectangle, right? And then we'll have to divide the integral value with the area of a rectangle. That is going to give us the average value, right? And from here, what we can write is that average average value multiplied with the area of a rectangle is going to be the integral value whenever your function is a positive valued function. Fine. So if the function is not a positive valued function, the integral value may not be positive, right? Only for positive valued functions this is possible. Here also, if the function f is positive valued, then we may write f average multiplied with the length of the interval is going to be the integral value. So this is there in the Riemann integration. The same idea we have extended for the functions of two variable, right? And with this idea, whenever you are given some function and you are asked to find out the average value, that you can do, since you know how to integrate these things, right? Next is properties of integrals. If you add two functions and you are integrating over a same rectangle, is aim as that of integrating those two functions separately and then summing it up. Okay, constant multiple of the function is going to integral value of the constant multiple of a function is same as that of the constant multiple of the integral value. Whenever you have this inequality is holding for all the values in the rectangle, the same inequality is preserved by their integrals as well, right? Now let us get into the next topic, that is iterated integrals. So this, how are we going to do it? So here is where we are actually coming into the calculation of integrals with the properties or with the fundamental laws, that is fundamental theorem of calculus and all those stuff we have learned in Riemann integration, we are going to apply those things into this to evaluate the double integrals, right? No more we are going to calculate Riemann sum and taking the limit. All those things will not be there, right? We are having a function of two variables over the rectangle AB cross CD. Okay, here we use this notation to mean that this function is integrated with respect to y, keeping x fixed, right? In a similar way, we can calculate the integral value a to b f of xy dx. We can calculate this integral with actually we are integrating this function with respect to x by keeping y fixed. This may also be done, right? So when you do so, you are going to get some value like this. Then you have to integrate this a of x with over the limit a to b, and that is going to give you the integral value of this double integral. Actually, if you have to do so, first you perform this alone. Keep x fixed and integrate with respect to y. That will give you some value, and that value shall be integrated with respect to x to get the entire double integral value. This ideology is known as iterated integral, right? So you may ask me, is it necessary that first we'll have to differentiate with respect to y and then integrating with respect to y and then integrating with respect to x? It may be done in the other way as well, right? So it is up to us. Now let us evaluate these two integrals. So the first one, we are asked to evaluate this integral, right? X squared y dy dx. First, let me do this one, x squared y with respect to y. So keeping x quantity fixed, we have to differentiate this y. That is y, sorry, integrate this y square upon 2 over the limit 1 to 2 dx. Right, this is integral 0 to 3. When you substitute, this limit is only for y, so it's going to be a 4 upon 2 x squared minus x squared upon 2 dx. So it is integral 0 to 3 by 2 upon x squared dx. So when you do this integration, you are going to get to 3x cube upon 2 times of 3 over this limit. So 3 gets cancelled, and when you substitute these things, you are going to get 27 upon 2. Okay, this is fine, right? For the same problem, let me do the other way as well. Okay, we rewrite this. Integral 1 to 2, integral 0 to 3, x squared y dx dy. So first when we integrate with respect to x, we are going to get integral 1 to 2. This is x cube y upon 3 over this limit. So this is integral 1 to 2. When you substitute 3, you are going to get 27. 27 upon 3 is 9. So 9y minus 0. So this is what we have. And this is 9y squared upon 2 over the limit 1 to 2. So this variable gives us that 9 upon 2 is a constant. So 4 minus 1, this is what we are going to get. And this is simply 27 upon 2. So the same result we are getting. Okay. And the second one, actually they are same, right? So this is A and this is B. The next problem, actually we have a theorem. This is Fubini's theorem. If a function is continuous on the rectangle, so here the function is a function of two variables, so we'll have to check the continuity of a two variable case. Okay, it is continuous in the rectangle, then this integral may be written in this fashion. Double integral over our function dA shall be written as integral a to b c, integral a to b, integral c to d f of xy dy dx, or integral c to d, integral a to b f of xy dx dy. It is up to us. Here the continuity may be relaxed just by restricting the function is bounded and it is discontinuous only at a finite number of smooth curves. Okay, so if it is relaxed to this case also, we are going to get the iterated intervals exist. We are not actually going to prove the Fubini's theorem, but what we have done in the Fubini's theorem is explained in this diagrams. Okay, first of all, we are integrating with respect to x in the sense we are finding this area, and then this area is prolonged, okay, to find out the entire volume. This may be done, or we may find the area along the y-axis, and then this may be extended. Okay, this may be done in either way. Here we have evaluated the area along the x-axis. Okay, actually in this picture we have evaluated the area along x-axis and then prolonging it. Okay, but here we are running it in the other way. Along y-axis we are doing, right? So to find the volume, this is what we are doing. That is what is given in these things that you may go through. Next we have an example that tells us to evaluate the double integral. Okay, so according to the Fubini's theorem, this may be a written integral 0 to 2, then integral 1 to 2. So integral 1 to 2 is inside, which means we'll have dy. Integral 0 to 2 is outside, that is why we have dx outside. Okay, now integrate this one with respect to y, keeping x fixed. So that is why we have xy minus actually 3y cube upon 3. This 3 and 3 gets cancelled, and then we are substituting the limits, and upon substituting the limits and simplify, actually when you substitute, you are going to get 2x minus 8, then minus, when you substitute 1, you are going to get x minus 1. So this is simply 2x minus x is x, minus 8 plus 1 is going to be minus 7. So we have integral 0 to 2 x minus 7 dx, and upon integrating this we are getting minus 12. Okay, now this integral shall also be written as integral 1 to 2, integral 0 to 2, then dx initially and then dy. Even doing this way, we are going to get minus 12, right? So actually what is given in this problem, that is diagrammatically represented using this. When you try to plot this, actually it is difficult for us to do it manually. You may make use of any of the computer tools to plot this. One thing that I can suggest you is that use GeoGebra. Okay, just give the function that will give you the surface. Actually, that will give you the surface, not the volume. This calculation it will not do. You can find out how the surface behaves. Next problem is integral y sine xy dA over this limit. So this is for x variable and this is for y variable. Okay, initially let me try to solve this in two ways. Integral 1 to 2, integral 0 to pi y. So if we are going this way, integral 0 to pi is inside, which means we'll have to, sorry, this is xy, not x comma y. So first we'll have dy and then dx. So if you see, you have y in two terms, which means you will have to make use of integration by parts. Let me take my u to be y and v to be sin xy. Sorry, dv to be sin xy. So my du becomes dy. My v becomes what? When you integrate sin, you are going to get minus cos xy. Here we have to treat x as a constant, so we'll have upon x. Right? So your integral 0 to pi y sin xy dy shall be written as uv, that is minus y cos xy upon x over the limit 0 to pi minus v du. So minus minus becomes plus, v is cos xy upon x over the limit 0 to pi and then dy. So here x is to be treated as a constant, so we shall take it outside, and when you actually give the limits for y, so it is going to be minus cos pi x upon x, and when you give this one 0 multiplied with some value is going to be 0. So plus 1 upon x integral 0 to pi cos xy dy, and when you integrate cos you are going to get sine cos pi x upon x plus 1 upon x sine x y upon x. So we shall write this as 1 upon x square over the same limit, right? So it is minus pi cos pi x upon x plus 1 upon x square sine pi x, and when you give 0 it is 0, right? We have calculated this one. Now we shall do the rest of the things, that is integral 0 to 1 if I am not wrong, sorry, 1 to 2, integral 1 to 2 integral 0 to pi y sine xy dy dx is now in the form of integral 1 to 2 minus pi cos pi x by x minus pi cos pi x by x plus 1 upon x square sin pi x. This one with respect to dx. Now you may ask me, this integration is becoming complicated. Yes, actually it is becoming complicated, but still we are able to do it. Let us see how. Okay, only the first one let us do. Let us take minus pi outside, so it is cos pi x upon x, right? And dx plus this one we shall write separately, 1 upon 1 to 2 1 upon x square sin pi x dx. Let us not do anything to the second integral. Let us try to do with the first integral alone. Okay, so here also we'll have to again make use of what, integration by parts. So for which let me take u to be 1 upon x and dv to be cos pi x dx. So therefore du becomes minus 1 upon x squared, and v becomes sin pi x upon x, right? So this becomes minus pi times of here actually what are we having, wait, here we are integrating with respect to x as x only, right? So we'll have upon pi, so minus pi cos pi x, okay, uv, so sin pi x u u is this, so this is what we have, okay, over the limit, and then minus we have taken minus pi already outside, so minus of minus pi integral 1 to 2, and then what, uv minus v du, right? So actually we'll have dx2, so sin pi x upon pi minus 1 upon x square dx. So this pi and pi gets cancelled, minus times of minus becomes what? So actually here let that be there as it is. Here when you try give the limits, what are you going to get? You are going to get 1 upon 2 sine 2 pi. Actually this pi and pi gets cancelled, so minus we have outside sine 2 minus, when you give this one you are going to have sine 1 times of sine pi. Here minus integral 1 to 2 sine pi x upon x squared dx, and this is only for this term, not for this one. This is there as it is. So plus integral 1 to 2 1 upon x squared sine pi x dx. The same thing we have here too. Hence, these two terms gets cancelled. And here, what is sine 2 pi? It is 0. What is sine pi? It is 0. So the answer is 0. Right? We have done this way. And the other way, if you go with the other way, integral 0 to pi, integral 1 to 2 y sine xy dx dy. Okay, this is solution 2. If you go this way, first we'll have to treat only x as a variable and y as a constant, so it has nothing to do with this y. So that will give you integral 0 to pi, y is there as it is, and when you integrate sine, you are going to get minus cos xy upon y, right? Over 1 to 2 and then dy. So when you give x is equal to 2, so anyway this y and y gets cancelled, minus we have outside 0 to pi. When you give 2 to y, it is going to be cos 2y minus cos y. So this is what we have. So it is minus times of, when you integrate cos 2y, it is going to be sin 2y upon 2 minus sin y over 0 to pi. Whether you give sin 2 pi or sin pi or sin 0, all the things are 0. So you are getting it to be 0. Right? In both the ways we are getting the same result, but one way was quite straightforward, whereas the other way was quite lengthy. But it happens. Okay. Next, in this problem, we are asked to find out the volume of a solid that is bounded by the elliptic paraboloid. Some equation is given between the planes x is equal to 2 and y is equal to 2. So whenever we are asked to calculate the volume of a solid, we are treating that in a positive sense. Okay. So we have to take, they have given between the planes x is equal to 2 and y is equal to 2. So 0 to 2 is the limit for x and 0 to 2 is the limit for y. Okay. From the given equation, we'll have to write down, we'll have to identify the surface. So from the given one, we'll have to express what is z. So z is 16 minus x squared minus 2y squared. Right? So here we are doing the integration by any means you can do, and you find that this value is going to be 48, whereas we have approximated this one in the previous lecture. Right? So hope I don't need to tell you the entire steps, as you people can understand. Next, this is a special case when we can factor f of xy into a function of two things. Okay, one function completely containing x, another function completely containing y. If you can do so, you can split your integrals as well. That is what this entire ideology tells you. Okay, if you remember this thing, it is more than enough, and with the help of that idea, we can evaluate this one. Double integral over r sin x cos y dA. So here we may very well see that x ranges over 0 to pi by 2 and y also ranges over 0 to pi by 2. We are splitting integral 0 to pi by 2 sin x dx and integral 0 to pi by 2 cos y dy, and we have calculated the integral, and that is this. Okay, and when you try to find out the surface it represents, you are going to get a surface like this. That is what. So if you can implement this idea, okay, actually you will have to write the given function as a product of two functions in which one consists only x and the other consists only y. If you can do so, you may very well use this idea to evaluate the previous integrals that we have seen. So that's it for the today's class. Thank you.